LearningMeasure.tv, science and engineering podcast with emphasis on measurement. Brought to you by David Archer and LearningMeasure.com. Episode 2, Wave Phenomenon. Hello. Welcome to the Learning Measure TV podcast, episode number 2. I want to start out by talking a little bit about some of the things I talked about last week, just a little bit of a review. Okay, last time we talked about frequency, sinusoidal things, period, that sort of thing. We're going to start off talking about that again, reviewing what we did. Okay, first of all, we just described something called omega, which is the angular, it's called angular frequency. I was about to say that last podcast, but I missed, which is equal to 2 pi times the frequency. Okay? That's how many radians, 2 pi radians in a circle. So this is how many radians per second in time, which is equal to 2 pi over the period. And from this you can deduce that, of course, the frequency equals 1 over the period. Okay, that was talking about periodic phenomena in time. You can also have something that's periodic in space. You can talk about k, which is the wave vector, which is 2 pi times the spatial frequency. This is the number, again, this is 2 pi radians per circle. So this is the number of radians per meter, which is equal to 2 pi over lambda. Lambda is a symbol its Greek letter lambda is used for wavelength. It's in meters. And from this, you can say the spatial frequency is 1 over the wavelength. So this is measured in radians per meter, radians per second. They're really similar quantities, they just have different units. And then we talked about sinusoidal waveforms. You know, things that are, let's, for this case, talk about e to the I. Let's say omega t, which equals sine omega t plus cosine omega t plus I sine omega t. This is another form of sinusoid. You can also talk about e to the I k x, where x is in meters. Well, so far we just talked about that's periodic phenomena, periodic in time, periodic in space. We also mentioned that the phase of you can say, for all sinusoidal quantities where you can have this function here, phi of t, called the phase of the sinusoid, whether this is e to the I or sine or cosine, this is called the phase. Okay, and we also were able to define the instantaneous frequency, even if this isn't linear or periodic, as 1 over 2 pi, okay, d phi dt. Or if an average frequency is equal to 1 over 2 pi delta phi, some change in phi over delta t. This is just the instantaneous version. This is average. You can actually do the same thing with the spatial frequency, you can talk about the spatial frequency at a point in the same manner, 1 over 2 pi d phi of x dx. Okay, that gives you the spatial frequency at a point. And if you want the wavelength, you can do a little math here. So the wavelength is going to equal 2 pi times 1 over d phi, the instantaneous wavelength. Okay, just like you could talk about the instantaneous period being 2 pi times 1 over d phi dt. Okay. Now, that's pretty much a review of what we learned, what we did last week. There's one more loose end that we need to tie up from last week. I had mentioned that you could measure the frequency by counting pulses. Well, let's say that you have some standard that's putting out some pulses at some period t standard, and you start counting pulses. And you really want to start counting at 0 for reasons I'll say in a minute. You start counting pulses, and then you count until you get to n standard pulses. Okay. In that time, the time elapsed is equal to n standard times the period of the standard. Okay. So let's say you wanted to measure some unknown frequency. Well, you'd count it too, starting at 0, say n unknown. You just start counting pulses, 0, 1, dot, 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 n unknown. Okay. So now you know that frequency is the number of things per second. The number of seconds is this. The number of things that happened is this. So the frequency is equal to n unknown, again starting from 0, over n standard. But this is t standard, but 1 over t standard is the frequency of the standard, so this is times the frequency of the standard. Okay. Well, that gives you an estimate of the frequency from the counts. How accurate is this estimate? Well, you can use standard uncertainty techniques. Let's just do RSS error of this equation, right? So this is F, delta F, uncertainty in F. We're going to RSS everything, so this is going to be square root. Derivative of this, so it's delta n unknown over n standard squared plus n unknown delta n standard over n standard squared. So this is squared times the frequency of the standard. Okay, doing a little bit of algebra, not much though. We often want to know what the uncertainty is relative to the frequency of the standard, so we just divide both sides by that. And since we're counting things, the uncertainty in the count is, let's say, plus or minus 1 or plus or minus a half, depending. We'll just say plus or minus 1. So this quantity here is the square root of 1 over n standard squared plus n unknown squared over n standard to the 4th power. Now you might think this is a small term here, but typically you want the frequencies to be close to being the same, so this is about the same order as this term. Okay, so let's say you had a 10 megahertz standard, or so that F standard equals 10 to the 7th hertz. Let's say you wanted to make a comparison to part in 10 to the 8th. Well, that means for this number to be a part in 10 to the 8th, this number has to be a part in 10 to the 8th. So for the second, we'll just ignore that. That means this thing here has to be 10 to the 8th. Well, 10 to the 8th, that's 10 seconds. This time here, typically in counter specs, is called the gate time. The time that you're counting pulses from your standard and your unknown. So you may have, for reasonable uncertainties, you might have to count for a very long time just from the uncertainty in the count. Minimum is plus or minus in half. Probably better to use plus or minus 1. So, and of course we haven't even talked about the uncertainty in the standard. I just wanted to point that out. That was a loose end from last week. Okay, we're going to return to our feature for this week, which is wave phenomenon, after this.
One of LearningMeasure.tv's sponsors is TradePub.com. TradePub.com is a site where one can sign up for a large number of free trade publications. If you'd like to support this podcast, go to the LearningMeasure.tv site, scroll down to the free publications link, and choose one of the magazines or one of the publications or one of the categories and sign up through that link. Each publication subscribed to through this link on LearningMeasure.tv website helps keep Learning Measure TV on the air. Thank you for your support.
Okay, now that we've reviewed last week, we need to talk about a new thing, is wave phenomena. A wave is something that travels in space and time. So you have some wave, I don't know, let's make it look like a sinusoid. Okay. At one point, this is varying in time. Let's imagine this wave moving that way with some speed v. So it moves that way. So this point will move from here to here. Let's say if this is in some time, vt. Velocity times time, it gives you distance, right? So if something, let's say you're driving your car at 10 kilometers per hour and you drive for an hour, well, that's really slow, but you'll go 10 kilometers. Okay, so that's velocity times time. Well, we're interested in the relationship between the wavelength and the period. Well, how far does this wave travel in one period? Let's say the period of this thing is t. Well, it's vt is how far it goes in one period. Well, one period, and by definition, is the time it takes the wave to repeat itself. So in this time, in that distance, it's back to the point where it started. So this has another name. This is the wavelength. Okay? So you've got the relationship that the velocity of a wave is equal to lambda over the period. Okay? Or any number of those you can solve for any one of those from even any two, you know. Okay, let's do this in terms of frequency. Well, v is also equal to lambda, well, in this case, yeah, let's get my eraser. It's lambda f. Okay, this is a relationship between the wavelength times the frequency is the velocity of the wave. Okay, that's true of all wave phenomena. Again, you might want to say, okay, what about the relationship between some of the other parameters you know in a wave? Well, you know k is 2 pi over lambda. So let's do some funny things here, like divide and multiply by 2 pi. So we got lambda over 2 pi equal times 2 pi f. Same thing, right? Well, this is k omega, sorry. No, that is right. This is k. It's 1 over k. It's omega over k. So in this case, k is equal to omega over v. So there's a relationship between the wave vector and the velocity and the angular frequency. So in general, you're going to have terms, let's say sinusoidal waveform. You're going to have something that looks like e to the I kx minus omega t. Okay. But now there's a relationship between, well, this is plus or minus here depending on which way it's going. Okay. So there's a relationship now between k and omega. So we can look at that. K is omega over v. So we could also say that omega is kv. So this is like e to the I k times x minus vt. Now you might say, well, look at this. This is the equation of something moving in at constant velocity times k. And you know that has to be the case because we started out with that. So we basically did that. And it turns out there's something called the wave equation that all waves follow. And you can say all waves are of the form x minus vt. You can prove that. I'm not going to do that here. If you've had some basic differential equations, you've probably seen this before. But that's not what we want to talk about here. So we're talking about a particular direction. You can say waves look like this or look like that. Okay. That's in one dimension. So we want to talk about, we're going to jump right away to 3 dimensions. Well, if a wave's, there's something called a plane wave. Plane wave is a wave where the surfaces of constant phase are planes. Well, might not surprise you to know that, well, something of the form e to the I kx x plus ky y plus kz z plus or minus omega t, that is a plane wave. Now, if you've heard of the term vector, is something that has 3 components. This is a 3-component thing. It has a different wave vector in all the 3 possible directions in space. It changes in phase this way, one way, this way, and then this way at different rates in general. That is the equation of plane wave. You can define something called a wave vector. A vector is a quantity that has more than one component, usually denoted with an arrow over it. That's a vector. equals kx. Now this is a symbol for a vector of unit length in the x direction, plus ky, y hat, which is unit vector in the y direction. So if we draw a three-dimensional coordinate system, x, y, z, x hat is a vector of unit 1, have length 1 in the x direction. This is x hat, in y direction, y hat, z direction, z hat. Okay. So plus kz, z hat, unit vector in the z direction. The position vector is going to be this, x hat, plus y hat, plus z hat, which describes any point in space. And we can define something called the dot product. The dot product, now these vectors can be represented by arrows. And the dot product is the magnitude of one times the magnitude, it's actually the projection of one onto the other. So it's a sine, it's the magnitude of this, magnitude of k, equals this, its length, kx squared plus ky squared plus kz squared. Okay. You can prove that with the Pythagorean theorem, just applied more than once. Same thing. R equals square root x squared plus y squared plus z squared. You should probably have seen this already. The distance from the origin of any coordinate system looks like that. So you can define something called the dot product, dot r, which equals magnitude of k times the magnitude of r times cosine theta. Okay. Now, that's just projection of one onto the other. But you can also define it like this. You know that we can define x hat dot x hat equals 1, y hat dot y hat equals 1, projection of a vector onto itself, and of course z hat dot z hat equals 1. And this dotted with that is 0, this dotted with that is 0, this dotted with that is 0. So all the combinations of anything with itself is 0, since these are at right angles to each other, so there's no projection. So you can also define k dot r equals kx x plus ky y plus kz z. Well, hey, that's this thing. So we can say, well, the general plane wave looks like this. E to the I k dot r minus omega t. Okay. We'll see why that's useful, hopefully next week. Okay, now I want to point out that that is just a plane wave. We had talked in a few episodes back about an isotropic radiator. Well, it propagates something called a spherical wave. And let's review that a little bit. If you have a point that's an isotropic radiator, that means it radiates equally in all directions. Because of conservation of energy, this is important, the power delivered to a sphere centered on that point is going to, all the power radiated from here is going to evenly distribute it over this sphere. The surface area of a sphere, 4 pi r squared. So the power per unit area is, well, we'll call that S for now, is going to be the power radiated divided by 4 pi r squared. Well, the wave, the voltage, this is power. Now we can, to simplify things, that the field itself is like voltage, the electric field. So the power is proportional to the electric field squared. So the electric, the electric field, or maybe even this could also be true of a sound field if you were talking about an isotropic radiator, acoustic isotropic radiator. The radiated form of this is going to be, this is what the phase looks like, e to the k dot r minus omega t. But instead of being proportional to 1 over r squared, it's proportional to 1 over r, because it's the square root. So this, some constant up here, will absorb the 4 pi into a constant. This is the form of spherical waves, whether electrical, acoustical, whatever kind of waves you can imagine. This is what a wave that's spherically expanding looks like. And what we'll do next week, what we intend on doing next week, is talk about, now that you know what a spherical wave looks like, there's something called the Huygens principle for electromagnetics, or even it would be true for acoustics, that if you have some wave front, some arbitrary shape, you can treat the wave front as a bunch of sources of spherical waves. Now, this might sound a little advanced. It is, but we're going to talk about something interesting that requires us to know a little bit about this next week. So again, we're talking about foundational stuff. But we now know basically how to represent plane waves and spherical waves. And next week we'll talk about how to represent general wave. Well, that's it for this week's version of learningmeasure.tv. Hopefully in our next episode we're going to be talking about a way to measure wavefronts and devices like antennas, maybe speakers, maybe, sound waves in water. And that's what, just a hint of next week. If you have any suggestions for what you'd like to see on this show, or you have a measurement-related question, email us at suggestions@learningmeasure.tv. And if you're a vendor who would like to be on this show, send us an email at vendors@learningmeasure.tv. Also, we're still looking for people who would be interested in interview on the podcast by joining part of our consultant network. The other thing, we're still looking for somebody, right now we're looking for somebody in the Las Vegas area who'd be interested in helping out with this podcast, or somebody who would be willing to travel to the Las Vegas area on weekends. If you lived close by, like in, I don't know, LA or somewhere. You also send an email at suggestions@learningmeasure.tv. We would love to hear from you. All right, that's it for this week. Hopefully next week will be more interesting. But like I said, this week and last week really were laying the foundations for what we're planning on doing next week. All right, see you next time. Bye.